So combining means and variances. Okay, so this I think conceptually it's pretty simple to sort of get an understanding of, but it has a lot of power behind it, and I'll sort of go through an example where not only can you use this uh, in designing a good efficient portfolio, right? But it has many different applications, right? I think so. One thing which comes to mind, I'm sure I'm stating it very simplistically, but I think there is a lot of application of this in inventory optimization, right? So one reason why Amazon is what it is as opposed to a brick and mortar retailer has a lot to do with this combining means and variances. Okay, and I'll sort of go through that example. Okay, so let's assume uh, you have salary and bonus details. Okay, so let's say you have a company. Okay, and you have a salary and bonus details of every one of the employees in a company, right? Some employees, of course, earn less on average, and some earn more, right? Which is pretty natural. Okay, so there is a variance. Okay, there is a variance around the average salary for an employee. Okay, so let's say so that's one data set. Okay, and let's say you have another data set with bonus information. Okay, so just like the salaries, the bonus information would also have some kind of a variance around it, right? Uh, so if you were to sort of combine these two, okay, to calculate uh, total compensation, okay, for all employees, right? So you would technically combine the means of those two distributions, okay, because it's a distribution, right? So anytime you have a data set which or a data series, okay, which has say salary details, of course you're going to have a mean, okay, which is the average salary of an employee, but you just add sum all that the entire column, and then divide it by the number of instances of salaries, okay, and you get your mean, and you of course have variance, and we went through as to how to calculate that, right? Same thing, you're going to have the bonus details, okay. So what there is that when you combine the two data series, okay, you can add up the mean, okay, you can add up the mean straight, so you can have as many data series as you want. Let's say you have a third data set which sort of describes something else in dollar terms, right? Let's say salary, bonus, and say benefits, okay, and maybe let's say you can quantify those benefits, and let's assume that there is some distribution around those benefits in terms of the perks, say an executive would get versus say no perk for someone who is a regular employee like me, for example, right? So you would have a distribution around that as well, right? So even if you have like say three distributions, you can combine the means straight away, okay, and you will get the total compensation, average total compensation of a typical employee in that company, right? You have standard deviation, which is the volatility around that mean, but you cannot add standard deviations, okay, so that's the fact, okay. The fact is that you cannot add standard deviation, you can only add variances, okay, and that is a huge implication of that, which I alluded to with that example of Amazon versus say a brick and mortar retailer, okay, but we'll go through that, okay. So you add variances of these two distributions, salary and bonus, okay. Let's say you can, and by the way, X is quantifying the salary by through a random variable, and Y is quantifying the bonus, okay. So you can add up to calculate the average. Variances, you have to sort of, you cannot add standard deviation, as I said, you have to add variances, and that's what we are doing. And there is this covariance term, okay. So first of all, what is this thing with 2, and then why do we add covariance, okay. So let's think about it conceptually, okay. So why the additional covariance term, okay. So let's assume for a moment that the salaries and bonuses for each employee are perfectly correlated, okay. That means the higher the salary, the higher the bonus one gets, okay. which most of the time is true in the real world, okay? And the lower the salary, hence the smaller the bonus, okay? So the folks who are on the higher end of the salary range will also get higher bonuses, so they will actually pull further away from the mean, okay? So that combined income is going to be a one big number and will pull further away from the folks who are not as high on the income scale, okay? Makes sense, right? So the near perfect correlation between salaries and bonuses makes the covariance term positive, okay, and hence adds to the individual variances of salaries and bonus, okay. I'm not sure whether it's clear, but I think if you think about it conceptually, it's pretty clear that the spread of individual data series, okay, which is salary and bonus, the combined data series spread, if there is a perfect correlation between that, is going to be bigger, okay. Makes sense, okay, because the one who is making more is also going to make more bonus, so it's going to get pulled further away. The one who is making less is also going to make less bonus. He is going to be further away from the mean. If you look at the distribution is like this bell-shaped curve, right? Assuming that, okay. Now let's assume that there is no correlation between salaries and bonuses, okay. And in that case, the covariance term is 0. And when would you have that? So let's say the bonus is basically distributed randomly, okay. Like there is no pattern to how bonus. So sometimes a very highly paid employee could get 0 bonus, and sometimes a very lowly paid employee could get a very large amount of bonus, right? So basically you can sort of see that the distribution is getting tighter, right? So if you randomize that thing, okay, the distribution is getting tighter because there is no correlation between these two, because we have purposely made it that way, okay. So the variability in total income is not as large as there was when there is a positive correlation between because the covariance term now is 0, right? Makes sense, okay. Now let's assume there is a negative correlation, okay. So we are now intentionally trying to narrow the gap in income by giving the largest person bonuses to the lowest salaried employee, okay. We intentionally, before this it was random, okay. Now we are intentionally making it thing. So now it's negatively correlated. So the highest person, okay. Let me go back to this thing. Maybe I misspoke here, okay. What I meant to say is that if it's random, the highest person can get any amount of bonus. Highest salaried person can get any amount of bonus. The lowest salaried person can get any amount of bonus, and there is no pattern, okay. So the covariance term goes away. So that means you have just the two variances you combine together. When you have negative correlation, that is when you intentionally go in and give the highest paid employee the lowest bonus, and the lowest paid employee the highest bonus, okay, that means there is negative correlation between salary and bonus. You know that your distribution is going to get the tightest, and that's where you subtract the covariance term, okay. So because of the negative covariance term, okay, so now you're going to have a much smaller variance when you have negative covariance, okay. So makes sense, okay, conceptually makes sense if you think about it, okay. And you can also always read up all here, okay. So the correlation between x and y is an important component of variability of the sum of x and y, and that's reflected in the relationship above, right? And that's what we are reflecting here. We are adding this covariance term actually dictates that. But what's the deal with this? This 2 times the covariance term, okay? So if you run through the math, okay, it looks a little bit daunting, but it's pretty simple if you break it down. And I'm not sure how many. So okay, so variance of x plus y. Let's assume this is just one variable z, okay. So how do you calculate the expected? So basically variance is z, if this was z, minus the mean of z, okay. So z minus the mean of z, okay. You square that, okay, and you take the expectation of that. That means you average it out, right? That's what you do typically when you calculate variance. You just had one variable. Let's assume this x plus y is called z, okay. This one will be replaced by z, this one will be replaced by z. This becomes like our typical variance equation if you go back, if you lecture in this notebook, in this note series, okay? And now you sort of try to expand, right? So basically, x plus y, so this is all we are doing is just playing around with this math. So now expectation of x plus y is basically expectation of x and expectation of y, okay? So we are just bringing the expectation inside because we know x plus y is the same as ex plus ey, okay? That's what we are doing here, okay? And we are expanding that, okay? So now the variance of x plus y becomes this, okay? And you can say x minus ex, y minus ey, we can just move around these terms, get square, okay? X minus ex is so now you sort of expand this term, okay? Because this, let's assume this is a, okay, and this is b, okay, and this basically separated by plus sign and it's square of that. So a plus a square plus b square plus 2ab. Remember those things you probably did a long time back, right? So you're basically just expanding this equation, and that's what we have done here. And that's where the two terms come, 2x term, that number 2 comes from, okay? And x minus ex is basically the variance of x, variance of y, okay? And this 2 times covariance term, okay? So pretty simple, okay? Okay, so let's see this in action, okay, in the next video.